Hello, in this tutorial, let me explain how you can create a 3D snowflake using the paper which was written by Gravner and Griffeath. And I'm gonna base the simulation algorithm based on this paper called Modeling Snow Crystal Growth 3 by these two guys. And this paper simply explains you how you can simulate a realistic looking snowflakes using several methods, some mathematical equations, and how you can do that through iterations, like this kind of fractal shapes with different parameters. So I've read this paper and kind of translated into Houdini's way of calculating things. So let me try to explain that, how you can do that. And before writing any Vex script, let me explain some brief algorithm how this works. So first of all, you need to have a grid, which is a hexagonal grid, looking like this. It is a hexagonal grid, but it's also a triangle grid if you connect each points with a line. So you make this one first, then you gotta make some group for several type of cells. So each cell has different meanings. The first type is the snowflake cell, which will be the cell that's gonna be shown as a result of a snowflake. So that's one type, snowflake. And there's also a type called boundary, which is on the edge, which is connected to a snowflake. The cell that's connected to a snowflake is called boundary cell. And the other cell, which is not boundary nor snowflake, is called air or non-boundary. And each cell has several variables included inside. One is called diffusion mass, which explains how diffused that cell is. Since the snowflake is a solid thing, solid ice cube or ice flake, the diffuseness is 0, so it's always 0 for snowflake. The boundary and the air changes by the neighbor's diffusion, so it's changeable, and that's kind of a one of the variables that you're gonna calculate through the iterations inside a solver. And the second property or variable called boundary mass, which shows you how I guess you can say the solidness of the cell. So again, the snowflake, the boundary mass of the snowflake is the maximum value since it's a solid, so in which you don't really need to know what the value is after it's became solid. For the other one, the boundary and the air is always like the air, like it's not solid at all, so the boundary mass is always 0. But on the boundary side, since it's attached to the snowflake, it's close to the snowflake, it kind of freezes. It got cold because of this center of snowflake. It will increase the boundary mass in order so that it becomes more solid and solid and solid. And once it goes over some specific value, which is written as beta in this paper, once the boundary mass is bigger than the parameter beta, then it becomes snowflake. Okay, and also only for the boundary cells, for this light blue cells, you need to have that information how much snowflake neighbors you have for each boundary cells, both for horizontal and vertical. For example, for this 0, 1, which is on top of the snowflake, these blues are all snowflakes, and these red cells are boundary cells. And you can see that the red cell on this position has only one connection on the vertical side, so, and no horizontal neighbors. So the left side of the number explains how many numbers of neighbors you have for horizontal direction. So in this case it's 0. For this one, you have 1, 2, 3 neighbors on the horizontal and 1 on the vertical direction. So that's that. And you need to have this kind of information for each boundary cells in order to continue calculation. Okay, so from here you this is the update method, like for each iterations, and what you need to calculate in order to make a snowflake. So first of all, this is like initial state. You have snowflake and boundaries and other air cells, and first of all you need to calculate for each boundary cells and the air cells the diffusion mass, how diffused they are. So more and more it's close to the snowflake, the diffusion mass become lower and lower. It becomes less diffused, meaning it becomes more, how do I say, going to be freezed. And there's 3 steps included in this calculation steps, and you can look at the paper afterward what kind of calculation you need to do. And the next step after the calculating the diffusion mass, the next step is called freezing. So this time you only look at the boundary mass, and for each boundary mass you calculate the property called boundary mass based on the diffusion mass. So the less diffusion mass you have, the more boundary mass you'll get. And you will calculate this also based on the neighbor count for each boundaries. And after you calculate the boundary mass, based on the boundary mass and the parameter called beta, which each beta parameter is different by the number of neighbor count. For example, the parameter beta 0, 1 is based on the number of neighbor cells for boundary cells, which has only 1 vertical neighbors on for snowflake. But beta 2, 1 is beta 2, 1 could only be used for the boundary cells that have 2 horizontal neighbors plus 1 or more vertical neighbors. And once the boundary mass is larger than beta, or some equations using beta, then it will become a snowflake. It will convert from the boundary mass boundary cell to a snowflake cell. And the last step for this calculation, for each boundary cells, the left boundary cells, in this case 3, you decrease the boundary mass, meaning you melt a little bit, using the neighbor properties, and also includes the diffusion mass to make it more airly. And that's kind of it. So that's a process that you're gonna make, that you're gonna have to construct using the Houdini. And let me try to explain you how you can do that. First of all, let's set some parameters, which you're gonna have a lot in this case, since if you look at the papers, as an example, it shows like, for example, in the introduction, page 2, you have this number of parameters, and you'll have more of these if you look at the other sections, the sections on the later sections. You have sample parameters written for each type of fractal cells, and there's more samples in the internet, I think, so you can check it out if you want to get the same kind of geometry using the different parameters. Okay, so let me go to the main network, and first of all, let's make a geometry. And let's make a null first. Let's color this, name this controller, and let's go to the edit parameter interface, and let's make some parameters here. Okay, first of all, let's make an integer called size, which stands for the size of the grid, the hexagonal grid. Could be range from 0 to 200, but could be more size you have, more resolution you'll get for the final result. But more you increase the size, the more calculation time you have to spend. So that's it. That's that. Okay. Now for the calculation parameters, let's make the first one is the beta, but then you have to have several beta based on the number of neighbor count for horizontal and vertical. So you have to have beta 01, beta 11, beta 10. Let me put this above here. Beta 20, beta 21, beta 30, beta 31. Now that's all for the betas. You might ask why you have only until 3 for the horizontal, and why you have only for 1 until 1 for the vertical. It's just that if it's more than 3 or 4 or 5 or 6, you all use beta 3 1, beta 3 the left side, B3. And if the right hand side, if the vertical connection is more than 1, it just could be 1 or 2, you always use 1 as a parameter. Okay, now next parameter is called mu 01. I think this is used for melting or attachment, or I don't know, freezing, maybe, forgot. You'll see later. Wait, mu 01, mu 10, mu 11, oops, mu 20. Yeah, this time for this simulation you'll have tons of parameters. It's a bit hard to see the right parameter by yourself. You might need some artificial intelligence here. Mu 30, mu 31, mu 31. Okay, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. Okay. Next is kappa. And for this one also changes depends on the number of neighbors. So kappa 01. Or sometimes all the kappa parameters become the same, sometimes different based on the number of neighbors. So, well, for this one, to make it more general, I'll just create every possible parameters. Kappa 10, kappa 11, kappa 11, kappa. Well, you can skip if you find it boring in this sections. I'm just typing parameters here. I know it's boring. I'm bored. Kappa 21, yes, okay. Apply. Kappa 30, kappa 30, kappa 31, and kappa 31. Okay. Okay, and that's all for parameters that's based on the number of neighbors. And also there's a parameter called rho, which is the default diffusion mass for air cells or non-boundary cells. And last, phi, which is used, forgot where, I'll see it later. Okay, so these are all float numbers. And apply, and let's go back to the network. No network. Okay, now first of all, as I said, you need to create a hexagonal grid, so let's do that first. I'm just gonna use a Bex to create a hexagonal grid here. So let's type a point wrangle, convert it into run over detail, and let's name it create hex grid. Okay, let's write some vex. I'm gonna open the editor by Alt E. And first of all, let's get the row parameter from the controller, which will be the default diffusion mask for non-boundary cells. So okay, and also let's get the size, which is an integer. Okay, and since this is the hexagonal grid, and I would like to make the plane xy plane to be kind of a square look, so each for size x and size y and size z will be different. The size x will be about size times 0.82, that could be adjusted by yourself, and size y equals size times 0.3, and size z is as it is. Okay, and float lengths, the lengths for the lengths between the grid, in between the grid on the hexagons, the distance between hexagons, the center of the hexagon, I mean. And also well, I think that's it. Let me check. Okay, I need to have one more parameter, I mean the variable for the lengths. I'll call this length z and length x, which is a distance between points, hexagonal points for x direction, and also I need to have another length parameter, length variable, which is called length z, which is on the z direction distance, which is about 0.1, 1.0 times cosine a times pi times 30 divided by 180. Okay, and let's make a grid for three-dimensional grid, three-dimensional hexagonal grid. So first, for the size, the z direction, and for the x direction, and finally for the y direction. Oops. Okay, and for the x, let's make a name shift x equals to j plus 1 module to 2 times 0.5 times length x and float shift z equals j times length z, and the position for each grid will be I times length x plus shift x t and shift z. And let's say I need to make a point, so int pt call at point 0 pos. Let's see if I get the position, the point here. Nope. Okay, spell mistake. What's wrong here? Okay. This is not an I, this is 1. Do I see any points? No. No, I don't see anything. And yeah, no points. Oh yeah, since I haven't put any parameters here. Okay, let me just put the size here, like 95. Okay. Now get the grid. Hexagonal grid. If you look from the top view, maybe I'll set it to something like 30 here. And from top view, you see that this is a hexagonal grid. Alright, and from the side view, you just have points on the vertical direction, and that's good. Okay. Now let's go back to the Vex editor and add some attributes to this point. Okay, first of all, let's set a initial freeze snowflake cell conditions to start with. So I want to have some centerpiece here, the snowflake cells to be placed on the center of this grid. So first of all, let's make a middle index, get the middle index of this grid, int mid x equals size x divided by 2 int mid y equals size y divided by 2 int mid z equal mint size z divided by 2.0 set and if I equals mid x and t equals mid y and j equals mid z, then set point group. Let's make this snowflake. Let's set this group to be a snowflake. And also let's make another group called, well, there's also within the snowflake there's also two conditions. If it's on the edge of the whole geometry or inside. And you only need to have edge snowflake for the calculation. So let's make an edge snowflake gloop as well. Snowflake to be 1. Since this is on the center and this is just one cells as an initial position, it's always a snowflake, also as well as a edge snowflake. Okay, and the other group that you want to set is the non-boundary, which I called air in the sketch. And for the snowflake cells, it's always 0. Okay. And if it's not on the center, then you can make it all non-boundary for this at this time. So set point group 0 snowflake to be 0. Let me just copy this. And edge snowflake is also 0, but the known boundary is 1. Okay. Also, let's set the attributes for this point at the snowflake cells. So let's use set point attrib diffusion mass. Since I have explained in the sketch, the initial diffusion mass for the snowflake is 0, so I'll set it to a 0. For the known boundary mass, you also set the diffusion mass, but the initial value here is rho. Oops. So, which I have get from the controller parameter, and so let's type rho here. Okay, now that's all for the snowflake and the known boundary. As a global attributes, you also need to set a set point group. First of all, the group, a boundary group. Now as an initial state, everything, either known boundary or center snowflake, is not a boundary, so set the boundary to be 0. It will change over time. And also set point attribute. You need to have a neighbor count. The neighbor count for the attached snowflake, named one type is horizontal neighbor count. The initial value could be just 0, then the other one to be vertical neighbor count, and the initial value to be 0. Okay, apply and close, and let's see at the geometry spreadsheet on the point section. And you have diffusion mass, horizontal neighbor count, vertical neighbor count, groove, boundary, edge snow. And if you look at the snowflake 1, you'll have a diffusion mass to be 0. Okay, let's set the rho here. Okay, could be any value for now. Let me see, could be like, the rho could be like 0.1, and if I look at, let me also set some betas and kappas and something like here. I'll just copy some parameter from one of the example in the papers. So let's see. I'm gonna use a parameter which is written here. This one. Okay, so first of all, the beta is these numbers based on the 0, 1 and 1, 0, 2, 0. And all the kappa and mu is same. And you have the phi to be 0, the rho to be 0.1. Okay, let's just write that down. So the beta 0, 1 to be 1.73, 1, 0 to be 3, 4. This one to be 1, 3, 4, 1, 1 and 1, and the mu is to 0.001. Now let's copy this, and every other mu is the same. Okay, and for the kappa, it's 0.1. Let's copy this, paste, 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 paste. And the rho and the phi is fine as it is. Okay, now let's go back to the editor, apply, go back to the geometry spreadsheet. Okay, the default diffusion mass for the non-boundary group is 0.1, and for the snowflake it's 0. Okay, looks fine to me. Let's go to the next vex. Now you have one center, one cell for snowflake as a starting point, but if you start from just one cells, there is a big chance that the growth will go exponentially high for vertical direction. So let me make some initial snowflake shape to be a little bit more bigger than 1 cells, something like 20 cells. Okay, so let's do that. I'll make a point wrangle here and connect this here. Okay, and could be a detail, I think. Maybe not, maybe not. Well, yeah, let me name this initial snowflake. So you just want to have a neighboring cells to be snowflake for the initial snowflake. So let's filter the group to be snowflake, which you will only look at the one snowflake cell point, and from that let's make a neighboring cells to be snowflake. Okay, so first of all, let's get the new points from this snowflake center point using the near points. Looking at using the p, the position, and since the one, the distance between points is equal to 1, so if you want 20 cells, you need to look like around 2 cells, so look at the distance of 2. But since this is a mesh-based calculation system, the 2 might not catch every point, so I'll add some offset value like this. Okay, and for each int NMP near point inside MPTS, let's first get the near point position. Yeah, and if the y value of the point is equal, or should I say abs point y minus npt pos y is less than 0.0, which means it's basically is on the same height. If the point is on the same height within this search direction, search distance, search area, then let's let it be a snowflake. So set point group snowflake to be 1, set point group edge snowflake to be 1, set point group non-boundary to be 0, set point group boundary to be 0. What else? Okay. Also attribute diffusion mass to be 0 for snowflake. Set point attribute boundary mass. Could be any value. Let's just make it 1. Set point attrib. I guess that's it. Let's look at it, and if you look at the snowflake values, you have around 20 snowflakes, and let's check it out if I got it right. So let's use the delete and get the snowflake loop and point and delete non-selected, and there you have 20 points, 20 initial snowflake points. Okay, it's good. Now the next thing you want to do is to calculate the for each grid points. You see that some point have some point have 9 neighbors for each point. Some point have like 4 neighbors if it's on the edge. And to make the calculation more precise, you only want to do the diffusion or the boundary mass calculation with the point which has the exact number of neighbor count of 9. So you have 6 horizontal neighbors plus 2 vertical neighbors plus yourself equals to 9. And if the neighbor count is not equal to 9, then you don't want to run the diffusion mass calculation or boundary mass calculation, since it will ruin the whole calculation process. So let's make a information for that. So for each point you want to do for each point, so let's put the point wrangle here, and let's say set neighbor count. Okay, and what you just want to do is int First you get the number of neighbors using near points with the something around 1.01, since the distance between points are 1 and you want to have some offset value 0.01, and you just add a new attribute called neighbor count, the lengths of the near points. Now okay, and if you look at the geometry spreadsheet, you'll have a variable called attribute called neighbor count, and you see most of the points are 9, but some are 7, 6 or 5, and for numbers that's not 9 you don't want to run the calculation for diffusion or the boundary mass, and you gotta to make the whole process more consistent. Okay, now that's all for the initial setup, and here comes the fun part, the solver, which is from here, the diffusion, freezing, attachment to melting. Okay, let's go inside the solver and let's write some calculation process. Now, first of all, you only have freezing cells and non-boundary cells at this time, so you want to have a boundary cell, which cells to be a boundary. So you want to find out which points to be the boundary cells, and let's do that searching first. Okay, so let's have a point wrangle and only look at the edge snowflake, since the boundary only connected to this edge snowflake. Okay, and first of all, let's set the initial value for horizontal neighbor count and the vertical neighbor count for each points to be 0. Okay. And let's also make a variable called distance, which is 1.01, which is kind of a search distance. And I'm gonna search both for horizontal position and vertical position separately for some purpose. Okay, so the first one I'll do the horizontal searches. Okay, and I'll call this HNPTS equals near points, and you wanna look only at the non-boundary group. Using from the position P, and okay, with the distance that you set above. Okay, for int I go 0 from, and within the HNPTS lengths, MPT equals HNPTS I the NPT, the near point position, equal 0.0 P MPT. If the absolute MPT position y minus point y position is less than 0.01, which means it's on the same height. Set the near point group to have known boundary to be 0. Change from known boundary 1 to 0 and wait for NPT position, and set point group 0 boundary to be 1. And also once this point becomes the boundary, it means you found a +1 neighbor count for horizontal position. So you want to have you want to add an attribute for horizontal neighbor count at the near point position +1, like that. So whenever the one point becomes boundary, this boundary point will have this horizontal neighbor count attributes to be added at incremented by 1. So you and you're gonna go through using all the points in the edge snowflake. You might find, I don't know, 2 neighbors, 3 neighbors, more than that. By writing like this, you can calculate that. Okay, that's for the horizontal. Let's do the same for the vertical, and I'll just copy this here and rename some of it. Now, first of all, since it's vertical, let's type it V here. And basically this is the same, and initial lengths, I'll type it here, VNBTS, and for this one, let's flip this to more than 0.01. So if it's more than that, it means the point is separated within the vertical direction. So if you're looking at this one, the near point will be either this one or this one. Okay, and the known boundaries to be 0 is as well. The boundary 1 is the same. For this one, I'm renamed this to vertical. And that's it, I think. And let's connect this one. And I have an error here. Spell mistake. And what else? What else? Okay. Right, and let's look at the geometry spreadsheet. And if you look at the... Okay, let me go back and go here. If you look at go on top, you see some of the points. Some of the point have horizontal neighbors to be 2, some to have vertical neighbors to have 1, and all the points that have either horizontal neighbor count or vertical neighbor count has a group boundary to be 1. And there are not snowflake as well. Either not a known boundary, I think. There a known boundary group listed here? Oh yeah, this one. Okay, these are all 0. Other one is all 1. Okay, now seems correct. Let's name this set boundary. Okay, next one. Now I need, since this is a solver and you're gonna run for each frame, you wanna reset some group values for edge snowflake here. Kind of a resetting. So I'm gonna use a point wrangle here. And let's name this reset edge snowflake. What you're doing is pretty simple. For each edge snowflake point group, you set point group edge snowflake to be 0. Okay, because you're gonna calculate it later, I mean with the next point wrangle. Okay, so you have resetted the edge snowflake. Now let's make the edge snowflake again. The reason why I'm doing this is because more and more you calculate through, more and more iterations you have, a more thicker and thicker the edge snowflake becomes. So you wanna reset each time it runs and just get the edge of the snowflake which is connected to the boundary, so that you'll have less calculation time, if it makes sense. Okay, now let's make a point wrangle and name this create edge snowflake. Now let's check this one, if all the edge snowflake has been resetted. Edge snowflake, okay, everything is 0, so it's fine. Now connect this to the create edge snowflake, and you can search the edge snowflake from the boundary you have just made above. Now the search distance is always, as always, 1.01, and you want to get the new points. Looking at the snowflake loop from the boundary with the distance search area, and for each new point get the new points npt and set point group edge snowflake. That's it. Oops. So since the edge snowflake is attached to the boundary, you look through the boundaries and from the boundary search for snowflake, and if there's there's a result point there, just set it to edge snowflake. And pretty simple. And if you look at the edge snowflake, no, I don't see anything. Okay, let me check. Okay, edge snowflake. Okay, you're looking from the boundary group. And BTS near points, snowflake distance. Seems correct. Let me go back. Oops. Okay, I don't seem to have any edges here, which is not correct. So let me check. Okay, let me see if there's a boundary, any boundaries here. Okay, boundary. Yeah, there is some boundaries here. There's also a snowflake here, so you should be able to get it. Maybe I'm making some spell mistakes somewhere. Edge snowflake. Non-boundary, boundary. Boundary. The distance here, the near points, snowflake, distance, set point group, the edge snowflake to be 1. Well, I guess this is the problem with the solver. If I click here and click here again, I might get the result. Oh yeah. So I have now the edge snowflake, which in this case, as an initial value, every snowflake cells become edge snowflake since this everything is connected to the boundary. So all the snowflake group value and the edge snowflake value should be the same one. Yeah. Okay. Now, enough for the setup inside the solver. Now you can start doing some calculations. The exciting part. Now let's get the point wrangle. And first thing you want to do is the diffusion. And there are some steps for the diffusion, so I'll call it diffusion 1 for the first one. And as I said in the sketch for the diffusion, you want to do for the air, which is a known boundary, and the boundary cells. So you want to look through all the cells except for the snowflake, which means you can filter the group boundary plus known boundary. Right. Okay. Now let's open up the attribute editor. Not the attribute editor, the scripting editor, Vex editor, and do some calculations. Now let's look at the paper briefly, what kind of calculation you're supposed to do. And you can go to this one, page 6, which explains what kind of calculation you need to do. So there are some steps that you need to follow until here. The first thing is this one. the diffusion mass calculations for each cells. And the second step is this one, which is using this is basically using the horizontal neighboring values. This one is considering the vertical neighboring values. And finally, the third step, you use this parameter phi to kind of reduce the exponential growth on the z direction, which it says in the paper. I don't really know what it's doing, honestly. But what I'm doing is just translating the code, translating the mathematical equations to the code, so I don't really care. Okay, now first step. Let's set the filter if the neighbor count, which you have set initially, is equal to 9, then you do the calculation. Okay, so let's set the variable distance as always, and let's set the initial diffusion mass to be 0, and int and PTS near points, which you have been doing a lot from the point position with this distance. And let's have a h diffusion mass as a variable here, since for the step 1 you're only looking at the horizontal neighbors and you want to calculate the horizontal diffusion mass. So for int I, you go through all the neighbors, lengths, and PTS. And npt equals npts I, the vector npt, the near point position equals to 0 p npt. Okay, and if the npt position y minus at mark p minus, the height difference is less than 0.01, which means if it's on the same height, then make a diffusion mass 0.0, get the diffusion mass from the point, near point, and add it to the h diffusion mass. And if you look at the papers, you have this signs. So this one is kind of a loop function in mathematical way of saying it. So you look all the neighbors with the for loop and add this diffusion mass. This dt is a diffusion mass at the neighbor position, and you add it to the temporal variable here, and finally you divide it by 7. So after you added all the values of, what you do is diffusion mass divided by 7. Okay, that's the first step. step 2. Now step 2 is this calculations. Now this value is the result of this one, which in this case H diffusion mass, and you need to get one more calculations looking similar to this, but this time it's for the vertical direction. So you can simply kind of copy this around until around around here, I think, and let's put it here and set the step to be here. Set the step 1 to be here, since you always want to calculate with the point which has 9 neighbors. Okay, and for the vertical neighbors, let's have another variable called count and float v diffusion mass, initial value to be 0, and you can use the same NPTS, near point variable here, and look at the same one, but here you flip the calculation. The large if the height difference is larger than 0.01, which means it's separated on the y direction, the height direction, and do the same to get the diffusion mass from the point on the vertical neighbors and add the v diffusion mass. In this case, also add the count as well. Or maybe I don't need a count. Why did I have a count here? Maybe I don't need a count. Sorry. Okay, so the final diffusion mass, which is this one. The final diffusion mass equals to H diffusion mass times 4.0 divided by 7.0 plus V diffusion mass times 3.0 divided by 14, and that is written on the paper like these. I'm just following this mathematical equations. This also explains that if like around here all the diffusion mass are the same, so the result of this calculation become always the same neighboring value. So everything is set as row as a default. So if every other neighbors have the same variable, same attribute row, then the result you get with this calculation is always the row. That makes this calculation make sense. And let's set the attribute diffusion mass for the point, the boundary point, to be diffusion mass. Okay, now that's the, oops. Okay, H diffusion mass. Okay. Seem to have an error here. Okay, seems okay now. Let's delete this count since I don't need this. Okay, and what it's doing basically is that it's calculated diffusion mass for each point based on the neighbor's diffusion mass, and you can see that the freezing mass, not the freezing mass, the snowflake cells. As I told you, that the snowflake cells have default value for diffusion mass to be 0. So this calculation makes that if the diffusion mass is lower than yourself on the near points, on the neighbor points, then yourself, the diffusion of yourself becomes lower and lower as well based on the neighbor's diffusion mass. If the diffusion got lower, it means it becomes less gas and more trying to be more solid. Now, if you look at the paper, you also have one more steps for calculating diffusion, so let's implement this as well. And I'll name this diffusion. I'm separating this point wrangle because it's using it's based on the value on the previous calculated one. I might not need to do it separately, but let me just do it separately for this one. You can try it out doing within the same point wrangle if you would like. Set the group filter to be boundary and non-boundary as well as the first one, and also use the filter if neighbor count equals to 9, then do the calculations. Now let's look at the papers and what you need to do. Now this one, it's a freezing state. AT means a freezing state at this position, at this iteration. T means time, I think. And the minus E3 and the plus E3 means it's whether it's on the upper direction or the down direction. Minus E3 means it's the ATX minus E3 means the freezing state, whether it's snowflake or not, on the bottom neighbors. ATX plus E3 means a freezing state, whether it's snowflake or not, on the upper neighbors. Consider that in your mind. Let's write it down in Houdini. Now, first of all, you need to get the point position, point number for the upper and bottom near points or neighbor points. So let's do that. For the bottom points, I'll just call DPT, down point number, equals to near point 0, point position from -1 on the y direction, and the search range of 0.01. And for the upper one, do the same with the upper direction. Oops. Okay. Now you get the near point number for upper and down, and let's also get the parameter called phi from the controller. Obj GO1 controller phi. Phi is used in this mathematical equations, this one. Right? Okay, and here comes the step 3 for diffusion. We need to check whether the upper point or down point is a snowflake or not. So let's use the attached status for the down point, the bottom point, using the endpoint group. If it is if it has a group snowflake at the DPT position, and a U, which is upper state snowflake, UPT. Okay. All right, and after that, let's also get the diffusion mass for yourself. Float. I'll just call DMX 0.0 diffusion mass, which stands for in this case it's this one, DT with the 2 apostrophes, just this one. And this one is the diffusion mass for the upper point, upper neighboring point, I believe, if I understand correctly. So let's get that. DMXU equals to 0.0 diffusion mass at the UPT. I guess the reason why it's only using the upper point is because the bottom and the upper always have the same numbers, since it's symmetrical. I guess that's the reason. I don't really know. Then let's calculate the final diffusion mass. Now, based on the paper mathematical equations, 1 minus phi times 1 equal 80 times dmx plus phi times 1 minus au times dmx au. Okay, I'm just translating this directly with the way of Houdini's syntax. Okay, and let's check 1 minus 5 minus AD times dmx plus phi times, okay, yeah, I think it's fine. And then assign this diffusion mass to be, update the diffusion mass with the final calculated diffusion mass. Okay. Now let's look at the geometry spreadsheet. Let's go first apply this here and click here. Go to the spreadsheet. Oops. And look at the point. Huh. Wait, I don't see any points now. It's weird. I have this points here. I lost the points here. How come? Where did I lost it? I seem to have some problem with the calculation within the solver. It's taking a bit too much time to calculate. Let's go look. And I seem to have a problem here with the diffusion. Okay, let's go back to the point. Okay, this is fine. Let's look at the diffusion. Okay, something must be wrong. Let me pause a little bit and look at. Well, somehow this part, the F diffusion, the set attributing part makes it really slow, calculating really slow somehow, which I really don't know why. Let me take a look at it a little bit more. Okay, I think I got the problem. Why I might be having some 2-byte characters somewhere which I cannot really see from here since I'm using the Japanese input language and input. Sometimes I mistakenly use 2-byte to type, and that might be causing a big problem here. So in that case, I just have to retype it. Let me do. Okay, now I rewrote everything exactly the same and it works now. I really don't know what's the reason why this things happens. It happens sometimes to me, and I'm assuming it's because of this language input issue, using the Japanese 2-byte character input. Well, now that it works, let's rename the step 3 to be diffusion 2, and this seems to work just fine, I think. Maybe not. Yeah, maybe yes. Okay, seems okay. And look, if you look at the diffusion mass, some value changes based on the neighbor value, and these are on the boundaries. Yes. Well, it's not always on the boundary. Could be on the known boundary as well, but most of the known boundaries value is right now 0.1, and but as you run through the iterations, it will change, I think. Let's do that. You see that these numbers changing as time goes, and it seems it's only changing on the bond. Is it only on the boundaries? Let me check. Yeah, it's only happening on the boundaries and not happening on the boundaries, and it's a bit strange. Let me take a look at it again. Okay. So it's supposed to be happening on both boundary and non-boundary group. And yeah, I think it should, the diffusion mass should change on the non-boundaries area as well. And the reason why it's not changing is because let's see. If I run this, let's look at the known boundaries and see if you have any diffusion. Oh, yeah. Okay, yeah. Even in the known boundaries, some values are changing, so it's correct. Okay, phew. Good. That's good. Wait a minute. Yeah. Okay. Now it seems it's working, and this one is also correct, I hope. If I run this on the known boundaries, yeah, okay, seems correct. Now that's for the diffusion, and let's do the freezing part. Now let's have the point wrangle again. And for the freezing, as I said in the sketch, only for the boundary cells, so filter this to the boundary. And let's write some script. If you look at the freezing part, which is this part, you're using a parameter called kappa based on the number of horizontal neighbors and the vertical neighbors, and you're calculating both bounding mass, the boundary mass, and the diffusion mass. So let's write this calculation, this mathematical equations in script. Let's translate this. Okay, first of all, let's make a function called get kappa based on the number of horizontal value and the number of vertical value, and float kappa 01 equals chf obj go1 controller kappa 01, and do the same for the rest of the kappas. I'll just copy this, paste. So you have 7 and 1 0 1 1 2 0 2 1 3 0 3 1. do the same for this one. 1 0 1 1 2 0 2 1 3 0 3 1. And if the h equals to 0 and b equal to 1, then return kappa 0 1. Else if h equal 1, I'll just skip this part since you'll know what I'm doing. Okay, I wrote it until here, until kappa 3 1, and finally let's make an else statement, and else then, well, it shouldn't be any other than this one, so let's just say 999. You're not supposed to have 999 as a result, but let's just write it like this. And float BM, which is a boundary mass, current boundary mass. You can get it from the float boundary mass, and also diffusion mass. Diffusion mass. Okay, and get the current horizontal neighbor count, which is minimum 3. Since if it's more than 3, just set it to 3. I horizontal neighbor count v minimum 1 I vertical neighbor count. Yeah, if it's more than 1, just set to 1, and float kappa equals get kappa hv. Okay, and float boundary mass is bm plus 1 minus kappa times dm, which is written on the papers, and the diffusion mass. Diffusion mass equals to kappa times dm. Okay, and let's update the diffusion mass and the boundary mass. Boundary mass equals to updated boundary mass. Diffusion mass is updated diffusion mass. Apply and connect it here. Okay, let's see. Let's run the solver a little bit and go back and look at the geometry spreadsheet and look at the boundary mass, which is here. And you have a boundary mass on the, I guess, on the boundaries position. Yep. How come you have only this number of boundaries? I think you're supposed to have more boundaries. I think. Wait. Boundary. Oh yeah, you have a lot of boundaries here. Although the every boundary mass has its value, so it's fine. Yeah, for each boundary cells. Okay, it's good. So that's That's a freezing part. Freezing. Okay, now next step is a attachment where you convert a boundary cells to a snowflake cell based on the boundary mass. If the boundary mass is big enough, then convert the boundary mass to the snowflake. So another point, wrangle. Yeah, this is really, this tutorial is really Vex intensive. You really need to know how this Vex works. But it's kind of a fun once you know it, I think. Okay, let's name this attachment. Oops. Attachment. And let's copy this get kappa function inside the freezing, since you'll do kind of a similar stuff. Let's copy this and open the editor and paste it and name this get beta, and just rename kappa with beta. I don't know if there's any replace, search and replace. I'm just gonna replace kappa with beta and replace all. Okay, seems good. Okay, now after doing that, float boundary mass. You want to get the current boundary mass. And also get the horizontal neighbor count and the vertical neighbor count as well. H equal I horizontal neighbor count, and also get the reduce the minimum or the minimum to be 3. So the maximum to be 3 using the minimum. So if it's more than 3, just set the 3. And also for the vertical, I vertical neighbor count, and you also want to get the min 1 HV. Okay, if now let's make a condition. If boundary mass is larger than get beta HMVM, or if H is more than 4 and B is more than 1, then set the boundary mass to be snowflake. And you can see the reason why I set this condition like this is by looking at the attachment section. This is the first condition here for this one. This is the boundary mass, the current boundary mass, and this is the beta parameter. And if the boundary mass is bigger than beta, then change the AT means AT is the freezing state, which means whether it's snowflake or not. If it's 1, it's snowflake. And one more condition: if the neighbor count for horizontal neighbor count is more than 4, and vertical horizontal neighbor count, the vertical neighbor count in the z direction and the y direction is 1, then you also have the freezing state to be 1, which means make it snowflake, which is this condition. Now, to convert the boundary cells to freezing snowflake cell, you need to first set the set point group snowflake to be 1, and set point group boundary pt num to be 0 since you're converting it, and also set point group non boundary to be 0 just to make sure, and also set point group edge snowflake to be 1 since it's connected to the boundary. The boundary is converted into the snowflake, means it's always on the edge. And finally, set point attribute and set the diffusion mass at the point number to be 0, since you're not, the snowflake's gonna be fixed to the solid state, and there's no more diffusion mass you're gonna be used in this snowflake cells, so set it to 0. Okay, apply, and I got an error. Where is it? Set point group snowflake. Enable to load shader failed. It's really not like the debug window is not really friendly. I can't really see where is wrong, which part is wrong. Let me open the editor and okay, in the 36 the line 36, where is that? I think it's around here. Okay, I'm missing parentheses here. Apply. Okay. Got it. Now, let's go to the next update function, which is finally a melting. Name this melting, and which will run on the boundary as well. Okay, and this time I'm gonna use a parameter called mu, and let's copy this again from above, get beta function here, and paste it here and replace the beta with mu and replace all. Okay, and name this get mu apply. Okay, and let's write some code. If you look at the papers for the melting, the function is pretty similar to the freezing part. In this case, in the freezing part, you are increasing the boundary mass. For the melting part, you are decreasing the boundary mass, which you are trying to make the solid value less solid, which makes sense by the name melting. Okay, so let's have the current boundary mass. Current diffusion mass. And a horizontal neighbor count. Vertical neighbor count. And mu using get mu function. Okay, and the new boundary mass, the updated boundary mass is calculated as 1 minus mu times bm, and the fusion mass equals dm plus mu times bm. Okay, and let's update the boundary mass and the diffusion mass. Boundary mass equals to mass diffusion mass to be diffusion. All right, and you can check the papers how the equation looks like. So this is the mu parameter, and this is the boundary mass, the current boundary mass, and this is the current diffusing mass. Okay, and we are almost there. And finally, after all the calculations, what you want to do is to reset the horizontal and the vertical neighbor count, and set all the boundary to be non-boundary, since you're gonna look for the boundary on the next iterations automatically. So point wrangle, and look at the boundary, and I horizontal neighbor count to be 0, I vertical neighbor count to be 0, set point group non-boundary at the PT non position to be 1, and set point group boundary at pt num to be 0. Okay. And that's about it for the solver. And let's name this reset boundary. Okay, and give a null. Let's name this out. Okay, and let's go back above, and as a result you are growing the snowflake cells time by time using the time frame, using the solver. So let's just get the snowflake part using the delete and the filter snowflake and the point and the non-selected, and this is the initial state. And from here to make it three-dimensional, let's make some hexagonal geometry, and I'll just do it. Maybe there's a way just to use a node, but I'll just do it in the Vex way, since this is a Vex intensive tutorial, which I don't intend to do that, but okay, never mind. Okay, let's name this create hexagonal geometry. And I don't need to filter the group, since I'm gonna do it for every points for the flow snowflake cells. And int prim equals add prim poly, and float lengths. The length of each side is 1.0 divided by square root of 3, and you have 6 sides, so for int I equals to 0 until 6, and float angle degree is 60 degree times I plus 30. Angle radius is radians or pi divided by 180.0 times angle degrees. And finally, the position of the corner is set point x times length times cosine angle radians p times y p dot t plus length times sine angle radians. And I think that's it. And finally, at the point at this position and at vertex for this prim in this point position. And also you don't want the current point yourself, so let's remove that. And there you have a hexagonal geometry. let's show the grid, I mean the line. Okay, good. Now I can extrude this to vertically, and the amount is 1 since I set the distance, every distance to be 1. And I can also maybe I can fuse it to reduce the number of points, and also put the normal to make it more crisp. And finally I can color this to, I don't know, maybe blue, since it's a snowflake. Okay, now let's try running this as a test. Right now the boundary, the hexagonal grid is really small, so it's supposed to run really quick. And yeah, it is growing as it's supposed to, something like this. Now at this point it's already looking like a crystal, snowflake crystal, but since the boundary is too small and the iteration is too slow, let's make it a little bit bigger than this. I'll make the size 95 and reset this, and also set the iteration, the solver substep, to be this one to be something like 9, and let's run with that. I'm gonna set the file cache here, since it's gonna take a long time to calculate, just to clear up. And just set it to normal for now, and let's do the calculation. Let's save to disk, and I'm gonna pause the video for now until it finishes and let you see the result. Okay, I'll pause it. Okay, we're almost there. Let me tell you a little bit about the parameter. So the more size you have, the more resolution you'll get for the snowflake, but the calculation time also grows exponentially, since this is like 3-dimensional calculations. But it's pretty, the result is pretty outstanding. So if you have a like more than 10 cores, you definitely should try it out. Okay, now the file cache has been finished. Let's load this and see the result. Let's play, and there you see the growth of a snowflake in 3 dimension, and it's pretty cool. It's pretty cool, even with the really low res 100 by 100 by 100, I mean 100 size of grids. Still looks really great. And that's about it. So this is how you can simulate the 3D snowflake using Houdini based on the paper by Gravner and Griffeath's paper. Okay. Thank you.